well, to meet in Zoom, but well. So, but essentially, what we did, we just discussed. We have discussed the fundamental theorem of algebra. So we used only one property of real numbers, namely that any polynomial of odd degree has a root. And another property of the complex numbers that any, well, maybe I can say it for real numbers, that any positive real number has a square root. So using these two properties, you can deduce that that any complex polynomial has a root, and this is exactly the fundamental theorem of algebra. Okay, so this was an application of some very basic Galois theory. Okay, so but maybe yeah. So, do you have any questions? So, are there any some topics that we should discuss more in more detail?
Что именно сдавать? Потому что часть мы разбираем, часть нет.
Ну,
там вот есть огроменный файл.
Да. Ну,
вот, что из него сдаем, что не сдаем.
Все.
Ага, понял.
То есть, если... ну, вы там смотрите, что там... То есть, ну, понятно, что все это просто много, то есть, вы там смотрите что-нибудь такое, что вам больше нравится.
Ну, то есть, просто что получается, то сдаем.
Да, да. Okay, if you don't have any suggestions, then we move slowly to the next theorem, namely to the primitive element theorem. Primitive element theorem. Well, let me start with some lemma, which is quite evident, but maybe you can lemma. So that no affine space is a finite union of proper affine subspaces if the base field is infinite. Yeah. Finite union. Finite union. Yeah. you see it's kind of some linear algebra. So we can assume the contrary. So we can assume that this affine space is a union of a certain proper subspaces Vi from 1 to n, and we may assume that n is minimal. Is minimal. And of course, it should be at least 2, yeah, because it's a union of proper subspaces. So we choose we fix just one of them, yeah. So for instance, one, and then we can claim that no of the rest of these subspaces contain, well, do not contain V1, yeah, because our n is minimal, so neither of these subspaces contains V1. Yeah, now we can choose some hyperplane, so some affine subspace of codimension 1, hyperplane V prime containing this V1. Yeah, and now we consider all the translates of this V prime. This is a certain one-dimensional pencil, and so of course no translates, no non-trivial translates of V prime contains translates of V prime contain V1, yeah, and maybe let me call it V double prime, yeah, yeah. So yeah, let me call it yeah. So let V double prime, yeah. So all right. So, and this means that this means that this V double prime is covered by the remaining subspaces Vi. Yeah. So.
But what if V prime is equal to V1? What if all our subspaces are hyperplanes? I mean.
Okay, that's no problem. We just take if this is already a hyperplane, then we take this V1 as V prime.
Okay.
It's not a problem. Yeah. So, and this means that this translate is covered by its intersections with the remaining subspaces. Yeah. So this is the union from 2 to n of the intersections of V double prime with Vi. And of course, this is contradiction because
Because the line obviously can be presented as finite union of the dots. I mean, we can proceed by induction, yes?
no, it's not even an induction. It's just a contradiction because the point is that we assume that n is minimal, but here we have a union of n minus 1 subspaces. I'm sorry. I'm sorry. I have missed some important thing, namely, you may ask whether this is a proper subspace, and that's what I want to.
Yeah, but we can just proceed by induction here, no?
Well, we don't really need to. We just say that so it's not doesn't contain v1, and also we want that.
It's minimal not for v that we took, but like as all slash numbers n go. Is that right?
Sorry.
When we said n is minimal,
Yes.
did you mean that n is the minimal number of proper subspaces that cover v, or did we mean that n is
In principle.
the minimal number of proper subspaces that cover n flat space?
Yes, we don't care about this particular v. We just assume that this n is the minimal possible n for some affine space.
Wait, then what is the problem with the v double prime?
The problem is that this may not be proper.
No, wait. If they're proper, why is it proper? Why?
Where is the contradiction?
M as a minimal for v for like some.
No. It's not for v. You see that this is it is minimal for for in the universe. Yeah. So.
Okay. Thank you.
Yeah. So, but the gap here in this argument is the following: that we have to. So we consider these non-trivial translations, but the point is that there is such a translation, translate v double prime, which is not contained in in v2 and so on vn. You see that here we use that our field is infinite. So here we need that our field has at least n elements. So we can choose such a translate, which is so. Suppose that one of translates is contained in v2. Okay, we move further. Then it is not contained in v2, but it may be contained in v3, and we move further. So this is there is because the base field say k, so that the field k is a order greater than n. Well, maybe even it's sufficient. Well, no, because 0 is not good because we want. Yeah, okay, it's greater than n. Yeah. So as our field is of order greater than 10, then we can choose a translate, which is not contained in these subspaces. Yes. So and this will mean that v double prime intersected with vi is proper. It is not the whole v double prime. Yeah, so it is strictly smaller. Okay.
And the unity of these
Hmm?
intersections.
Yeah, and then you see that as this is this subset does not meet V1. Yeah, so and it is and this means that it is contained in the union of the remaining V2.
How about talking about the last line?
Yeah.
Maybe there's a union of these intersections.
Yeah, you see that we just you see that we only so for each I we claim that it is this intersection is proper, and as this intersection is proper, then we present V double prime as a union of proper finitely many of n minus 1 proper subspaces, and this contradicts the minimality of n. Okay. Okay. So next theorem is due to Steinitz. It is. It says that an algebraic extension admits a primitive element. Maybe I should write what is a primitive element. So it's definition. An element. So an element alpha is primitive. For an extension L over K if it generates L as a field over K. So if L is generated by alpha. And the claim is that an algebraic extension, field extension L over K admits a primitive element. Primitive element. If and only if there are only finitely many intermediate subfields in this extension. If it has only finitely many intermediate extensions. Sub-extensions. Okay, so suppose first that there is such an element which generates L over K. So suppose that L is generated by an element theta. Then so the claim is that any intermediate subfield in this extension is obtained by adjoining certain so any intermediate subfield L over K is obtained by obtained by adjoining coefficients, by adjoining coefficients of the minimal polynomial over that coefficients of the minimal polynomial by adjoining adjoining to what? To adjoining to k coefficients of the minimal polynomial of theta polynomial of theta over this intermediate subfield. Maybe let me any intermediate subfield f is obtained by adjoining coefficients of the minimal polynomial theta over this field f. Yeah, namely yeah, maybe we can so denote this indeed. So let f prime be such a subfield, be well, be such a subfield. So you see, so we start with f. We consider the minimal polynomial of theta over f, and we adjoin the coefficients of this polynomial to k, and we call this f prime. So f prime is what is obtained by adjoining the coefficients of the minimal polynomial over f. Yeah. So strictly speaking, so you can definitely claim that f prime is contained in f, but we want to show that actually they coincide. Okay, so maybe we should call this g, this minimal polynomial over f, and at the same time this g is a minimal polynomial over f prime. Yeah. So this means that so we can just compare degrees of
theta over f and f prime.
yeah. So we can compare degrees of say L over f and L over f prime. Yeah. So what is this? As you see that actually this is this L is generated by theta. Yeah, so L is we assume that L is generated by theta even over k. So it is also, you can consider this as a field extension of theta. Yeah. So it is, and therefore this degree coincides with the degree of its minimal polynomial. Yeah. And on the other hand, again, here we can say the same thing. Yeah. So that L is generated by theta over f prime, and therefore this of course this polynomial is also irreducible, so it is also a degree of g, and therefore this degree coincide, and the fields are embedded, and therefore they.
G is the minimal.
Yes, G is a minimal polynomial. It's here. Yeah, and therefore the fields coincide. They're the same. Now, okay, so so we have such a correspondence, and we can conclude that there are. You see that G divides the minimal polynomial of theta over k. Yeah, and there are only finitely many divisors. Yeah, so there are only finitely many divisors of this minimal polynomial over k, and therefore there are only finitely many intermediate subfields. Okay. Next, we want to prove the converse. Yeah, so that if there are only finitely many subfields, intermediate subfields, then there is such a a primitive element. Yeah, so conversely. Here, unfortunately,
How did you get that from G being the divisor of the minimal polynomial of theta over k? There exists on the intermediate subfields.
You see that we just have shown that any intermediate subfield is generated by the coefficients of the minimal polynomial over that subfield. So so any intermediate subfield is determined by the minimal polynomial of theta, which divides this one.
And then it comes to the amount of divisors of.
Yeah. So well, you can say that it is maybe not in infinitely many. It's less than or equal to 2 times degree of this extension. Okay, yeah, so unfortunately we have to consider, well, there is another way to prove this, but let me be more direct in a sense. So we have to consider separately two cases. The case where the base field is where the field is finite, and the case where the fields are infinite. Yeah. So if L so what do we want? Yeah, we want to assume that there are only finitely many. Yeah, maybe I should say that it is evident here that if an algebraic extension is infinite, then there is no primitive element. Yeah, so we can always assume that our extension is finite. So yeah, so if our k, well, if L is finite, then its multiplicative group is cyclic. And therefore, of course, there is a primitive element. You just take this generator. Of course, this is, and then what you get. So if k is infinite, and then you just apply lemma, yeah, because all intermediate subfields are proper k-vector subspaces. Yeah? And we know that a finite unit of proper subspaces cannot be over an infinite field, cannot be the whole space. Yeah, so then apply lemma. Okay. And now this is
L cross
is cyclic. Is cyclic. It's yeah. It's the invertible elements form a cyclic group. It is generated by a single element.
Excuse me, do you mean that L is finite over K in the second case, or?
No, finite as a field, as a field.
I mean in the second case that L is in K is infinite or L.
Well, I mean L, but if you want to say, well, maybe okay. If you want to be more careful, then you can you should consider the case when K is finite.
Mm-hmm.
If K is finite, then but L is infinite, then there are infinitely many intermediate subfields.
Okay.
So actually, this is not the case. So yeah, maybe we should. All right. Maybe okay. So if K is finite and there are finitely many subfields of L, then L is finite as well. Okay, because you see that any we haven't discussed this, but maybe we should. What do you know about finite fields?
They defined by cardinality to isomorphism.
Up to yeah.
And characteristic.
Yes, but I mean that any for instance, any algebraic extension of a finite field is a Galois extension.
Yeah.
And therefore, so if you well, actually, yeah. So any algebraic extension is any algebraic extension is a union of finite extensions, and it is if this extension is infinite, then it is a union of infinite sequence of. So there are.
How do you spell this word? Is cyclic?
Yeah, this is cyclic. Yeah. Yeah. So once again, if K is finite, then L is finite as well. If we assume that there are only finitely many intermediate subfields, because any algebraic extension is a union of finite extensions, and a finite union of finite extensions is again finite. It is, yeah, so we can assume that L is finite. And if L is finite, then its multiplicative group is cyclic, and therefore it has a primitive element, even over the prime subfield. Okay? Is it okay?
I mean, the second case where K is infinite.
Infinite.
Yeah, the other case, so.
Okay. Yeah, so if K is infinite, then we consider the intermediate, the proper intermediate subfields as K-vector subspaces. So you see that they are K-vector subspaces, and their union is not the whole.
So we can take primitive element
From the rest, yeah, from the complement to the union, yeah. So take any element is primitive in the complement. So this is the complement to the union of all intermediate subfields is precisely the set of all possible primitive elements. So, and this shows that the primitive elements are quite. There are some. Yeah, the most of elements are primitive. Okay. Yeah. Now we can prove the primitive element theorem. Yeah. So the primitive. So the claim is that any separable algebraic, any separable finite extension admits a primitive element. So any finite separable element, extension, separable extension, okay, admits a primitive element. So we're going to use this Einstein's theorem, namely, we just have to check that any finite separable extension admits finitely many intermediate subfields. So maybe Einstein's.
Last time we had proved that any finite separable extension is contained in some normal extension.
Yes.
So we can use just Galois correspondence.
Yes, yes, that's exactly what I'm going to do. So we can assume that, yeah, extending L, we may assume that this extension is Galois, and then well, finite, yeah, is finite. Galois is Galois finite, and therefore subfields in intermediate subfields are in one-to-one correspondence with subgroups of the Galois group. And this group is finite, so there are only finitely many intermediate subfields. Okay, and so of course, a non-separable extension may also admit a primitive element. For instance, of course, so an example is so if you take any field and consider rational functions, then of course you can take any subfield generated by any rational functions, for instance, x to the p, and so this extension of this so suppose that the p is the characteristic of k, and of course this extension is not separable, but it is it has a primitive element, namely x. Yeah. So this extension is not separable, but what you can show that if you generate a field by two independent variables, so consider rational functions in two indeterminates, and consider it as extension of the subfield of rational functions in x to the p and y to the p, then this extension does not contain a primitive element. So of course it is also inseparable, yes, and it does not admit a primitive element. Okay. Yeah, actually, this in some versions this theorem is quite old, but maybe its proof is not that old, in the sense that even already Galois used some kind of this theorem to construct his theory, but there were certain problems with that. Yeah, so maybe just to complete the story, maybe I should at least formulate a normal basis theorem, but before that I need some general algebra fact. So what? Yeah, maybe. So does everyone know Krull-Schmidt theorem? No. Okay. Let me state it. Maybe later we will discuss some more direct proof of this normal basis theorem, but let me just explain some very explain it as a very direct consequence of some general fact. So theorem. It is due. Well, there are several people. Krul, Remark, and they stated it in very different settings and generality, but so we deal with modules. So we assume that A is an associative unital ring, is an associative unital ring. Next, M. M.
We did just prove the theorem of the primary element.
Yeah, it's a theorem of
Yeah.
primitive element. Yeah.
Of a primitive.
Yeah.
And how exactly do we get from the action of intermediate subfields and subgroups the existence of the primary element?
You see that this means that there are only finitely many subgroups of a finite group, and this means that there are only finitely many intermediate subfields. And by the Steinitz theorem, so okay, so we assume that M is an A module of finite length. Should I say what does it mean finite length? Of finite length. This means that it admits a finite filtration with simple quotients. So then M is a finite direct sum, is a finite direct sum. Sum of indecomposable submodules of indecomposable A modules these indecomposable A modules are determined uniquely up to permutation, more or less. Yeah, so it's yeah, and these determined uniquely up to isomorphism, permutation, isomorphism, permutation. And so on, yeah. Okay, should we prove this theorem, or you will read this by yourself? Okay, so the reference is you can read this in Lang algebra in any sufficiently recent edition. I don't remember exactly, something like well, 2000 should be okay. I think 2000 something. but even in 1990s, I think already good. Okay, and so how will we use this? We will use this in the following way. So corollary. So we assume that x and y are A modules of finite length. And x to the n, so it's direct sum of n copies of, so n is an integer, and direct sum of n copies of x is isomorphic to direct sum of n copies of y. And of course, we want to conclude that x and y are isomorphic. Then x is isomorphic to y. Yeah, and the proof is evident. So proof, you just decompose x into sum of indecomposables. So let x be isomorphic to direct sum of pi I with certain multiplicities, and y be isomorphic to direct sum of say qi qj, say to the direct sum of nj.
Excuse me, the conditions n is strictly bigger than 1.
Well, well, I mean, it's also true even if.
Yeah, but we can
Well, no. Yes, if it is still true, even if n is equal to. Maybe it's not that interesting, but.
Okay. For some 1.
No, we fix. We fix n. N is fixed, yeah. So n is well, doesn't matter. Okay. Yeah. So we assume that we decompose this. So here pi and qj are indecomposables. Indecomposable. And then we get that the direct sum. So if we sum up n copies of x with itself and n copies of y, we get that here we get the I to the yeah.
P, Y, and Q, J are
Indecomposables. Indecomposable modules, yeah. So they are isomorphic Qj and Jn, and then by Kruller-Mark-Schmidt, Kruller-Mark-Schmidt, we conclude that we can renumber. So we can renumber Qj so that
it's Kruller-Mark-Schmidt.
this one, Kruller-Mark-Schmidt theorem. It says that Schmidt, Otto Yulievich Schmidt. know, this Arctic investigator. So that Qi is isomorphic to Pi and min is equals to nin. Okay. Well, and now we can conclude that that the multiplicities are the same, and this precisely means that x and y are isomorphic. So, okay. So now, so now the theorem. Well, we don't need this. So normal basis theorem. So it's due to Noether, and this proof is due to Doring. So let H be a finite group. Group of automorphisms over field K. Automorphisms of a field K. And we set small k to be the fixed field of H. So this is the fixed field. Then then this field big K as a module over the group algebra of H is isomorphic to the group ring as a module over itself. So K of H. So what does this mean? This means that there is an element theta such that so what can you do with this theta? You can map the group ring to the field K by sending, so if, for instance, if you have certain formal linear combination of elements here, you can send this to the sum with the same coefficients of theta, which is twisted by these elements. Yeah. So, and the claim is that you can choose such an element theta so that this map is an isomorphism. Is an isomorphism, and this means that such that what does this mean that this is an isomorphism? This means that the orbit of theta is forms a basis. So so H orbit, the H orbit of theta is a basis is a basis of big K as a vector space over small k. Okay. So you see that from the point of view of this action, the field itself becomes something like the group ring. And how to prove this? The proof is almost trivial modulo this corollary, namely modulo this corollary and some other fact, namely we can consider, first of all, we know that K is not just a module over the group ring, yeah, it is also module over the twisted group ring, where because we can multiply the field by its own elements, yeah. So it is a module over this algebra model, and K. Yeah, and on the other hand, K, this group ring as a module over itself, is isomorphic to, yeah, maybe we should make, oh, doesn't matter, yeah. So this twisted group ring as a module over itself is isomorphic to direct sum of copies. We know, you know that any well, let me recall you that any module over this ring is isomorphic to module to a direct sum of copies of K. It is some kind of Hilbert's theorem 90, or some version, or Speiser's theorem, or Noether's theorem. Okay, and in particular, this twisted group ring as a module over itself is also isomorphic to a direct sum of copies. And if you count the dimension, you will find that is isomorphic to sum of the cardinality copies of this H. Okay, and this is on one hand. On the other hand, what can we say about this ring? So now we can say that K as a big K as a small K vector space is just well, some finite dimensional vector space, which is K vector space, and therefore what? Therefore we can identify K of H as Yeah. So is direct. Yeah. So we can say we can use. Well, for instance, we can choose a basis of big K as a vector space over small k, and then present our twisted group ring as a direct sum of copies of the usual group ring. Well, and there will be the same number of copies. So as this is decomposition as a k of h modules. So you see we have two isomorphisms, and we put them together. So k in this power is isomorphic to the group ring. In the same power, and then we apply corollary. So this corollary implies that, because you see that the order of the group and degree of extension are the same. Yeah, so corollary and the equality. So we get an isomorphism of K and K of H. So it is.
Excuse me, could you please explain one more time why twisted group algebra is isomorphic to kh, small kh, as a kh model? Yes.
This? That's a good question. Yeah, that's a good question because, yeah, so because maybe it's not that evident. Yeah, so fix a basis. Yeah, so suppose that alpha 1 and so on, alpha n is a k basis of k. We want to construct this isomorphism. Yeah, so we just maybe we could proceed. Yeah, so we want to construct a map in the opposite direction. Yeah, so this this way. Well, let me write to the n. Yeah. So we just have to explain what is our map on jth. Yeah. So for instance, we can put here jth coordinate. So k of h, and we want to embed this into k of h as a module over the group algebra. Well, you just apply this these elements here to alpha j. Yeah. And you may ask why this is an isomorphism. Yeah? To see that this is an isomorphism,
the second
sorry?
map is the multiplication by alpha j, or
No, it's
the projection.
yes, sorry, yes, it is a multiplication by alpha j on the right. Because on the right, because we want this to be a morphism of modules over the group algebra. So what we You see that dimensions are the same, so the only thing we have to ensure that this is injective. Yeah. So this is injective, and how could we check this? So well, this is more or less clear because you just you can look at or maybe it's enough. No, or maybe it's enough to show that it is subjective. Yeah, it's subjective. Yeah, so, yeah, this is subjective because we want to get here all elements. Yeah, yeah, it is. Yeah, but this is, for instance, you take what do you want? We want an element here, an arbitrary element here.
Can you just compare dimensions over k small? Because
No, dimensions are the same. But you see that to make sure that this is an isomorphism, you need to show that it is either injective or surjective. Yeah. So, and maybe with surjectivity it is slightly easier. Namely, you just take. Yeah. So you get here. Yeah. So here you get all elements of type.
Okay. Yeah. We can just
Alpha.
say alpha gt minus 1.
Alpha. You see, we get here alpha j h times h. Yeah. Ah no, sorry. Yes, yes. So and these elements form a basis. Yeah. So when you vary.
Yeah, but
when you vary j, this will give you k a basis in k times h, and as h is arbitrary, you get the whole space here. So it is surjective.
So this text in bubble considered the proper intermediate subfields.
Sorry?
So this text considered the proper intermediate subfields of SQ vector subspaces, and where does it belong? It's
I mean, it's
part of the theorem.
yeah. So this. Yeah, so this is surjective. And well, that's it. Yeah, because everything is finite dimensional. Okay, so yeah, and now we may pass to.
excuse me, one more question.
Mm-hmm.
We have this map in the theorem. Is it also a ring map?
No. You see that H need not be commutative.
Yeah, but I mean, it can have a kernel. Okay, all.
You mean here?
Yeah.
No, it's always it is an isomorphism.
Okay.
So it is called normal basis theorem because the this basis of big K as a vector space over small k is constructed as an orbit. It's called a normal basis. Normal means that it is a Galois orbit of some element. Okay. So of course it's morphism just as modules over the group ring, group algebra. Okay, so yeah, so I think we have discussed all principal theorems. Now we can pass to some more specific things. Specific means that, for instance, we want to know what are how do abelian extensions look like. So you see that when we say when we talk about Galois extensions, then we deal with the Galois group of this extension, and so the question is what this Galois group could be. And in the case when this Galois group is commutative, the extension is called abelian. So it should be first Galois extension, and the second it should have a commutative Galois group. So abelian extensions. No. So this is the Galois extensions. Galois extensions with commutative Galois group. Yeah. So do you know any examples of abelian extensions?
Every quadratic extension.
Very quadratic. Okay, and more.
Any finite field is extension over
Every extension of a finite field of a finite field. Okay. Commerce extensions. What do you mean by commerce extension?
I mean every finite extension of finite field.
Any algebraic? Every algebraic.
Okay.
Well, for finite it's also true. Okay. Yeah. So maybe we should start with this one. Yeah. So, what can you say about finite fields? Finite fields consist, well, except of zero, of course, and they consist of roots of unity. Yeah, because in some power they are equal to 1 if they are non-zero. And that's the point. That so essentially, so the claim is that adjoining roots of unity. So when you consider extensions of finite fields, you just add roots of unity. Yeah. So I claim that this can be generalized. Actually, any. So more generally, adjoining roots of unity gives an abelian extension. Okay. By the way, why?
Because Galois group is included in group of automorphisms or maybe endomorphism of cyclic group of roots of unity.
Wait, you see that you should be careful because if your extension is, it need not be cyclic because it may be infinite, for instance. For instance, yeah. But you can adjoin not all of them, yeah. But on each step, when you adjoin only one root of unity, then of course you're right. The resulting group will be finite.
So just taking limits.
Yes. So so because so maybe it's because the Galois group is embedded into into the group of automorphisms. Maybe we should be more precise. Yeah. So roots of unity, say J, zeta, say gives an extension k of zeta over k. So we can consider k of zeta over k, and it is embedded into what? Into the group of automorphisms of the group generated by this root of unity, and this is a cyclic group. This is a finite cyclic group. Finite cyclic, and therefore its automorphism group is just well, roughly speaking, this is Z modern, and this is
Just multiplicative.
yeah, just the group of invertibles in this. Yeah. Okay. Yeah, and so actually, in a sense, in some cases, one can show that this is really the only source of. Well, there are some examples where roots of unity or their versions. Their versions are the only source of abelian extensions.
What do you mean by versions?
But well, if you want to, okay. So, but what do you mean by roots of unity?
Solutions of equation x power n equal to 1.
When you say power, this means that you deal with something like multiplicative group. Yeah. So, but you can consider some other group. In some sense. So, what does this mean? So, so the roots of unity. So we have something like a multiplicative group. Multiplicative group. Well, maybe group. And you have this. This means that there is some operation, yeah, and you can multiply something on itself several times, yeah. So raise it to nth power. And the roots of unity is the kernel of this. But actually, you may start with something else. So, well, maybe I should write this maybe in the following way. So we assume that so we need certain commutative group. We want maybe we need so you see that we have to start with some field K and some Galois extension. Say with the group G. So we need. So we assume that we have some commutative group. It's like multiplicative group of L. So we want that the group G acts on this F. So endowed with the G action. And also we need some kind of coordinates. Coordinates means it's a commutative group. It's a commutative group, but not just a group, but some group endowed with the G action. And also we need some coordinates. Plus coordinates. Coordinates means that it means that maps to from F to, well, roughly speaking, to L, but these maps should commute with the G action. Commuting with the G action. So, well, in the case of multiplicative group, well, there is no big deal to find to define this coordinate. You just embed it to. Into L and okay, and yeah, and what do we want? So now, if we have such a group, then we can define its torsion. Torsion means that if this commutative group, so the torsion is well defined. So it's like multiplication by. It's multiplication in. We use additive.
It's finitely generated or?
No.
Okay.
No. It's usually it's huge. The best example is you take separable closure of K as L. So example L is a separable closure, and yeah. And if you look at the multiplicative group, it will be huge. But the point is that the torsion is not that huge. So you can define this Fn. Okay, and so why?
And what does F the left index N is?
And torsion in it's the kernel of the multiplication by n.
And the map on the right is the
10.
by 10.
Yeah, just adding an element with itself n times. Okay. So yeah, and to make so what do we want? We want so how to construct an abelian extension? How could we construct an extension of K? So we can, for instance, we can add these. Well, roughly, one says to add n torsion, but we cannot add n torsion because this is just some group somewhere. But what can we do? We can add its coordinates. Yeah. So so we say that K of Fn is F on this side. So K of coordinates of elements of Fn. And we want to know whether this extension is abelian. Yeah. So then, what do we want? We want that we want to impose one more condition, namely that automorphisms of extra condition that automorphisms of this group as G module, so that automorphisms of Fn is commutative. Yeah. Yeah, maybe we can modify a little bit this. Yeah, maybe it's better to work in some. Yeah, maybe I should consider something more precisely. So here we directly pass to automorphisms. Yeah, but instead of automorphisms, we can start with endomorphisms. Yeah, and the same works here. So we consider, let us denote by R the endomorphism ring of F. Wait. Let us do it like this. Yeah, just all endomorphisms. You see that in the case of the multiplicative group, it is it can be quite huge. Well, then we should stop here. So, and the next time we will come back to the roots of unity. Yes, that's a good question. Maybe we should. Do you have any ideas how could we do this? Technically, yeah. Discord.
Yeah.
Assuming the amount of visitors, we're probably under 10 participants.
Yeah.
Maybe 10, 15 maximum. Maximum 15 of us. So Discord will work properly with the screen share.
Okay.
Well, screen share doesn't allow like writing on a whiteboard for anyone who's not sharing the screen.
can use a draw or something like that.
But maybe someone knows how to, but I don't have my laptop with me, but I don't understand the problem. Why my my Google Meet doesn't work? I mean, there's
Well, this also happened to me before when